Okay then, in this session we'll look at the normal distribution for the first time. We'll spend a bit of time on it because there's a result that we will see later which explains why the normal distribution keeps coming up. It's sort of all over the place, and that result will tell us why. But for now, we'll take a first look at the normal distribution. Okay, and we start by defining the standard normal. Okay, it's traditional to write the standard normal as random variable as capital Z. So the standard normal distribution has this form: 1 over root 2 pi exponential minus 1/2 Z squared. Okay, now we're actually going to be dealing with a family of distributions which are called normal distributions, but as a practical matter, we always end up having to convert back to the standard normal. So knowing the standard normal is important. Okay, so this is the form of the PDF for the standard normal distribution. Now, so this is part of the graph, right? The graph extends infinitely in both directions. This is a part of the graph, and we see that most of the area is under the curve is in fact from z equals minus 3 to z equals plus 3. Okay, and note that it's symmetric. Okay, right? Why? Because you're squaring things there, so x and minus x gives you the same result, and it's peaked at x is equal to 0. Okay. So, otherwise we often refer to this as the bell curve. Okay. Right, and its expectation is 0. And it's right, you can see this by considering that if you want the expectation of the standard normal, well, you integrate z from minus infinity to infinity, z times the PDF. Well, this function here is even, right? Whether you put in z or minus z, you get the same result, right? So then you're multiplying it by z, which is an odd function, right? So this is an odd function times an even function. So overall, it's an odd function, the integrand. And you're integrating an odd function over a symmetric interval. So it's going to integrate to 0. We could, in fact, do a substitution and work this out, but we can just see it right away without doing any integration if we want. Okay. All right, so let's say that I wanted, for the standard normal, I want the probability that z lies between minus 2 and plus 2. Okay, well, what do I need to do? I need to integrate from z equals minus 2 to plus 2, the PDF for z. And then I look at this and I realize that I can't do it in terms of the standard elementary functions that we used in Calculus 1. Okay, so how am I going to do this? Well, what we do is, well, I guess in the old days you would have used a table. Nowadays we have calculators, we have online sources, and we can just plug the values in, right? And capital Phi is the CDF, the cumulative distribution function, right? So we calculate the CDF for z at 2, and we subtract the CDF for z at minus 2, right? And we get 0.9545. So, once again, 95% of the area under the curve is from -2 to +2, right? If we include from -3 to +3, we're going to get 97 something percent, right? Probably, right? So almost all of the area under the curve is between -3 and +3. Okay. All right. So you're going to do the calculations. You're actually going to use the CDF. Yes.
This would be the same answer if we just put in those limits in the PDF, right?
Yeah. If we could actually do the integral,
yeah,
then these are the numbers that we would get this number. Yeah.
Why can't we do the integral?
Well, see, if this was exponential of minus something z, we know how to do it. If it was exponential of minus something z squared and there was another z outside, we would know how to do it. But this, we don't have an antiderivative for it in terms of elementary functions. Okay. All right, so we would use a table, or we would use an online software or a calculator which would give us these values. Okay. All right, so for the purposes of the exam, I'll give you a z table. Okay. The variance and the standard deviation, well, the variance is 1, and so the standard deviation is 1. So again, if we go back here, 1 means 1 standard deviation from the expected value of 0. 2 is 2 standard deviations from the expected value of 0. So, you know, again, we would say that almost all results will lie between -3 and +3 standard deviations from the expected value. Okay. Okay. All right, I already said that.
The standard normal is like a continuous random variable?
Yeah, this is a continuous random variable, right? Okay. Defined for, it's non-zero for all z, all real z. Okay, the moment generating function, right? What's the moment generating function for z? It's the expectation of the exponential of tz. So you integrate from -infinity to infinity, e to the tz times the PDF. That gives you your integrand. And, okay, so you have to integrate that. We do a bit of manipulation with the exponents there. Note that t is not being integrated here, z is being integrated. So you could actually pull the t outside. Okay. And now, what do you have here? Again, you can't do that integral, but you can. It turns out to be well, okay. If you do multivariable calculus, it turns out to be √2 pi. Okay. So if you haven't done calculus 2, you haven't seen how that works. So anyways, these cancel, so you get e to the -1/2 t squared, right? So if you are working on some problem, yes?
I'm a little confused. We took u because z and t both are variables, or are we taking t as constant?
Oh, I took t is a constant, so if I let u be z minus t, right, then yeah, that's a substitution. Okay. All right. So if you're working on a problem and you calculate that the MGF of your random variable is e to the -1/2 t squared, that means that your random variable is in fact the standard normal. Okay. Now that was the standard normal. So let's generalize that. to a family of distributions that we call normal random variables. Okay? So the more general form is this. Right? The PDF takes this, the PDF for x, if it's a normal random variable, is 1 over root 2 pi sigma squared, exponential minus 1/2, x minus mu over sigma all squared. Okay? Now if you calculate the expectation and the variance, it turns out that sigma then would be the standard deviation and mu would be the expectation. All right? So let's say you have this PDF from the standard normal, right? And you just want to move it over so that its peak is at x equals 1. All right? What's the PDF that would give you that? Right? Nothing else about the curve changes. It just shifts over so that it peaks at 1. What would you do? Right? You would let mu equal 1. You would keep your variance as 1. Okay? All right? Okay. And once again, when you have this is more general. Okay? So there's an entire family of normal random variables. But when you want to do calculations with this, you will not be able to calculate antiderivatives and so on for this. So you transform it back to the standard normal, and then you read from the table or use a computer. Okay? Okay, so this is the way you do it. Supposing I have a normally distributed x, right? So it's got its own, it's got an expectation mu sub x, and it's got a standard deviation sigma sub x. Okay? So that's x. That describes x. Now, if I create a new random variable, I take x and I subtract off its expectation. Remember, we already discussed this when we standardize any family of random variables. If we take the random variable and we subtract off its expectation, and then we divide by its standard deviation, the result is a new random variable with expectation 0 and variance 1. Right? And in fact, in this case, where x is a normal random variable, the result is also a normal random variable, and in fact, it's the standard normal random variable, which we usually call z. Okay? So this is the way we calculate the probability, then that x lies in an interval from a to b. Right? We say the probability that x takes a value between a and b is the same as, now we apply this transformation, x minus its expectation divided by its standard deviation. So all through the inequality, we say a minus mu over sigma, so that should be less than or equal to. Now x minus mu over sigma is z, less than or equal to b minus mu over sigma. So the probability that the random variable x lies between a and b is the same as the probability that the standard normal, for which you do have information and tables and software and so on, it's the probability that the standard normal lies between a minus mu over sigma and b minus mu over sigma, where mu is the mean for x and sigma is the standard deviation for x. Okay, so you do this transformation, And then you can use the CDF for the standard normal to do your calculations. Okay, so let's do an example of that. Okay, so you've got a normal random variable. It's not the standard one, but it's normally distributed. And it has an expectation 100, and it has a standard deviation 10. What's the probability that it takes a value between 80 and 85? So how would we do that? Okay. Well, we'd say, what am I being asked for? I'm being asked for the probability that x lies between 80 and 85. Okay? Well, that's the probability that x minus mu over sigma lies between 85 minus mu over sigma and 80 minus mu over sigma. Is that okay? All right then. What was mu? Mu was 100. So 80 minus 80 minus 100 is minus 20, and 85 minus 100 is minus 15, right? And what's x minus mu over sigma? That's how you standardize the normal random variable into the standard normal random variable. So this is now the standard normal random variable, right? Okay, what was sigma? Sigma was 10. So minus 20 over 10 is minus 2. And minus 15 over 10 is minus 1.5. So what this is saying is that the probability that this random variable, this normal random variable, lies between 80 and 85 is the probability that z takes values from minus 2 to minus 1.5. Right? Right? So this is the probability that x is taking values between minus 2 to minus 1.5 standard deviations from the mean. Okay? Okay, so this is what we worked out here. Now, how do I calculate the probability that z lies between a and b? Well, you take the CDF of b and you subtract the CDF at a. Right? So somebody has helpfully, right? And then if you look that up in the table, suppose, you'll get this number. Okay. All right, is that all right?
Professor?
Yeah.
Can you go up here for a second?
Yeah.
Wouldn't it be 5 minus 2 minus 5 minus 1.5? Oh, never mind, never mind.
Okay.
Take a second first.
All right. Okay. All right, so let's try again. The heights of students aren't going to be approximate. They're not going to be exactly normally distributed, you know. Students are distinct and the curve is continuous, for example, right? But let's say we get a histogram of heights of students and we say, okay, if you'd have a histogram and you try and fit a normal curve to it, and you find that the best fit is for a bell curve where the expectation is 170. Right, so you calculate the mean, and you say, okay, I'm going to suppose that the mean is a good approximation for the expectation of a normal distribution, right? And you calculate the standard deviation, okay? And we say, how many have heights less than 160 centimeters? Oh, okay. Again. Okay, so I'm concerned with x lying between, well, I guess minus infinity. Okay. So that's another reason it can't be exact, right? There are no there are no negative heights. And 160. Okay. Okay, usually we just write this as the probability that x is less than or equal to 160, right? Okay, now let's do our transformation. That's the probability that x minus mu over sigma is this equal to 160 minus mu over sigma. Right, and what's this? Well, we did the transformation so that we would recover the standard normal, right? So what's this? Okay, so mu is 174.5. And sigma is 6.9. Okay. Okay, so this is the probability that the standard normal takes values less than minus 2.1. Okay. Let's go back here for a second. Right, so that's about 2. So, right, so it's all the area under the curve from minus infinity all the way up to 2 standard deviations. Okay, that's what we're talking about. Okay. So we find our handy dandy calculator or a table, and this is the number that we get. Okay, so if this is a probability that that students have a height less than 160, then out of 1,000 students, we expect 17 or 18 students. Right. Okay. We discussed the moment generating function for the standard normal. What about the family of normal random variables? What is it? So once again, it's the expectation of e to the tx. Okay, so e to the tx, the function, times the PDF, and then you have to integrate from minus infinity to plus infinity. Okay, and all right, so there's a bunch of substitutions, and this is what you'll get. All right, you get e to the mu t, e to the 1/2, sigma squared t squared, right? For the standard one, mu would be equal to 0, and that term wouldn't be out there, and sigma would be equal to 1. So that's what we had before. Okay, so now if you want to calculate higher moments, for example, that becomes fairly easy to do, right? It's differentiating exponentials, we know how to do. Okay, now yeah.
Do you need to know the derivations for how to find moment generating?
No, you don't need to know the derivation. Okay, so let's try an example. X is normal with parameters expectation mu and variance sigma squared. Now y equals ax plus b. So y is a new variable. And I would be interested in knowing, for example, is it a normal random variable? Right? X was normal. But if is y equal ax plus b normal, for example? Well, if I can find the MGF for y, and I know what the MGFs of normal distributions look like, then I can tell whether y itself is normal or not, right? Okay, so okay, so how would we go about doing this? The MGF for y is equal to the MGF of ax plus b. How is that related to the MGF for x?
A will be the multiply the MGF of x with a and then add b to it.
Yeah. Okay, right. So how do you do the right? The MGF of ax plus b is related to the MGF for x by, so you take the MGF for x and you replace t by at. Evaluated at. Remember from our discussion of MGFs previously, right? And you get a factor of e to the bt outside. Okay? Now, what's the MGF for x? So you have e to the bt times, what's the MGF for x at t? Well, I want the MGF for x with t replaced by at, right? So that's e to the mu, t gets replaced by at, times e to the 1/2 sigma squared, and t gets replaced by at, so at squared. Okay. Okay. So now it kind of looks like the MGF for a normal random variable, right? But let's play around with the exponents a bit. That's e to the a mu plus b t, right, these two terms here, times 1/2 a sigma squared t squared. Okay? What was the MGF for a normal random variable? It was e to the expectation times t times e to the 1/2 variance t squared. So that's e to the, well, this a mu, that's e to the something t plus 1/2, something that I could call a variance, t squared. Right? Except now, the variance is a, instead of being sigma squared, the variance is a squared sigma squared. And instead of the expectation being mu, the expectation is a mu plus b. Okay? So, if x is a normal random variable with expectation mu and variance sigma, then this new random variable y, which is equal to ax plus b, is also a normal random variable with expectation a mu plus b instead of mu, and with variance a squared sigma squared instead of sigma squared. Okay, so this linear transformation of a normal random variable gives you a new normal random variable. Okay. Well, let's look at another problem involving normal random variables. Supposing I have x is normal and y is normal, and they're both independent. What does independent mean? Their joint PDF is the product of the individual PDFs. Okay? What about, what does the MGF of a sum look like? If x and y are independent, then the sum x plus y has what MGF?
Just the sum of
the sum?
the product.
The product. Right. Right. Okay. So, all right. So, if x is normal and it has in expectation mu x and variance sigma squared x, and y is normal and it has an expectation mu y and a variance sigma squared y, and they're independent, then let w equal x plus y. We're going to find the MGF for w, because we know what the MGFs of x and y are, so we should be able to find the MGF for w. And we'll see if we can characterize what w is. Okay? All right, and once again, as you said, okay, sorry, that should have been w, not z. The MGF for a sum of independent, it's important that it's independent. The MGF for a sum of independent random variables is the product of the individual MGFs. Okay? So, we worked out just now that for a normal random variable x, its MGF looks like e to the expectation of xt times e to the 1/2 variance of x times t squared. And similarly for y, this is what the MGFs of the individual normal random variables look like. Okay, so the MGF for x plus y is this right-hand side times this right-hand side. Okay, so I put them together. Now I group the terms which are multiplying e to the mu xt and e to the mu t, I put them together. And e to the 1/2 variance of x squared t squared and e to the 1/2 variance of y squared t squared, I put those terms together. And what does this look like? Well, this form reminds me of the form for the MGF of a normal random variable. Except now, I would expect e to the expectation times t. So that new random variable, that new normal random variable, has expectation mu x plus mu y. And here I would expect e to the 1/2 variance times t squared. So the variance of this new random variable is the sum of the individual variances, right? So if I have a random variable x, normal random variable x and normal random variable y, and they're independent, and I add them together, I get a new random variable. That new random variable is itself normal, and its expectation is the sum of the individual expectations. And its variance is the sum of the individual variances. Okay? Okay, so one thing that we do with the normal is we use it to approximate the binomial, right? Normals are often, we understand that the underlying distribution is in fact not normal, right? Underlying distributions of heights are not normal, but we do the approximation. We approximate using a normal, right? The underlying distribution in some cases might be binomial, but under some circumstances, the normal can be used to approximate, to get approximate results when the underlying distribution is binomial. Okay? Okay. So let's say that x is a binomial random variable, right? You might recall that x then has parameters n and p. N was the number of trials, and p was the probability of a success in each trial, right? And in that case, the expectation of x was np, and the variance of x was npq, where q is equal to 1 minus p. Okay, you might remember that. All right? So then, as the number of trials goes to infinity, so we're imagining a vast number of trials, okay? And we standardize our x, okay? So x minus mu over sigma. Mu for binomial is np, and sigma for binomial is root npq. So we take x minus, so this is the standardized, this is a standardized, right? And then if we let the number of trials go to infinity, in the limit as n goes to infinity, this standardized x in the limit becomes the standard normal. Okay? So, we'll discuss more next time about the use of normal distribution when the underlying distributions are something else, right? Anyways, for now, let's take to this example. So a coin is tossed 100 times. We call getting an H a success. Okay, here n then is 400. I seem to be assuming that it's a fair coin. So P is 1/2 and Q is 1/2. Okay, so what's the probability of getting between 185 and 210 H's? Okay, so until this session, you would have said, oh, it's binomial, right? So how would you do this as a binomial? Using the binomial distribution. How would you do it? Right, you'd say, right, okay, so you'd say something like, the probability of k successes is what? Well, you're going to toss it 400 times, and you could get exactly k successes, and then 1/2 to the k, 1/2 to the 400 minus k. Is that right? Does that look right? Okay, and then these are exactly the same, so I guess we can talk that. Okay. And if this is very large, then the computations may be on a hand calculator. Probably a computer now would do it very quickly anyways, but maybe by hand it might be a bit of a pain, right? Okay. Then again, if this went to 40,000 and these numbers were very large, that's an awful lot of summations that you need to do. Right? And this binomial coefficient involves factorials of very large numbers, perhaps. Again, these non-trivial things. Okay. Well, all right. So, okay, now in our, what's the other way of doing it is to do an approximation. So mu, what's right? We want x minus mu over sigma to normalize the random variable, and then the limit as n gets very big, we claim that it's close to being the standard normal. Okay, so what's mu? Well, you're tossing 400 coins. You're tossing a coin 400 times the probability n times p is 200. Okay? And your variance is npq, so n times p times 1 minus p. It's 100. Okay? So, we approximate with the normal. We say that the probability that x lies between 185 and 210 is approximately, we do this normalization procedure. 185 minus mu over sigma. X minus mu over sigma becomes the standard normal. And then 210 minus mu over sigma. Okay, so that is approximately the probability, right? It's approximately this probability. Okay, and then that probability is the probability that the standard normal lies between minus 1.5 and 1. Okay, so how do you calculate that? You calculate the CDF at 1 minus the CDF at minus 1.5. That's what you would have in your tables. Yes?
So how would we know that a particular question can be approximated with normal? Like, what is a particular feature of a problem that I can...
Okay, well, why can we approximate with it? Well, okay, so we're going to see probably in the next session a result which tells us when we can do things like this. Okay. All right. So, like I said, okay, so the CDF at 1 minus the CDF evaluated at minus 1.5, you look in your table and you'll get 0.7745. Okay. Okay. So that is the that's our introduction to the standard normal, and we will hopefully in the next session see why it's so important and why it keeps coming up everywhere. Yeah.
Would this still hold if the coin is not fair?
Well, your NPQ would be different, right? But yes, you could still make an approximation. Okay. See you next time.